Here we have a system where two masses are connected by a thread that runs over a pulley, and one of the masses, small m, right here, is sliding on an inclined surface which makes an angle alpha with the horizontal. Another mass, signified by the capital M, is hanging from the threads, creating a tension which is uniform throughout the string, because we assume the ideal condition where the string is massless and inextensible. In addition, we also assume that the surface the mass small m slides on, it has friction and is characterized by the friction coefficient mu. For simplicity, we are abbreviating the kinetic friction coefficient as mu. The question then would be to solve the system for the acceleration. So we know the acceleration of the system would be characterized by the Newton's second law, which states that F equals to ma. In this case, this particular formula, F equals ma. By the way, this m is not the same as the small mass m that we have in our system, but it's just a generic mass. So this is Newton's second law, and we'll have to apply it in two cases. That means for these two objects separately. We'll draw the force body diagram, and then we'll use that to make our job of vector additions easier. So let's get started. So first, let's start with the bigger mass m. It has gravity acting on it, and of course we are assuming that capital M is greater than small m. Later we'll talk about the necessary conditions for this object to slide in this direction. So beforehand, we are assuming the acceleration takes place in the vertical direction for the bigger mass, big M, and for the smaller mass, small m, the acceleration is directed at this direction. So that is our assumption, and we have chosen these two directions to be consistent because the string is inextensible. So therefore both of these masses must be in harmony while they are sliding in the same direction. Now for the mass big M, we have two forces acting on it. One is the gravitational force, which is mg, and the other one is the tension force along the string, which is written by T. Now we choose our direction, our positive y-axis, to be in the given direction, so this is going to be plus y. So what we have is mg minus t is going to be equal to capital M times A. So that would be our equation number 1. What about the equation for the small m? So we'll have to apply the Newton's second law once again for that mass small m. So the case for small m is a bit complicated because it's not just simply a one-dimensional problem. We have to set up another coordinate, and congruent to our chosen coordinate for the mass capital M, we can choose the appropriate coordinate for small m as follows. So this is going to be our y, okay, and let's say this is going to be our z direction. So this is only applicable, I should write, for small m. I could have also said, for example, in fact, let's do that. I could have also called this side x and that side y. This y is of course different from this y for the capital M. And what we have is, given a mass small m, we can draw all the forces, all the external forces that's been acting on it, So for example, there is a gravitational force which is given by small m times g. There is a tension force acting in that direction, and of course there's a normal force acting on the object by the surface, which is n. Now we can decompose the gravitational force mg into two directions. One is against m, and that should balance the normal force, so this is going to be alpha as well. So this is mg times cosine of alpha, and this is going to be mg sine of alpha. So what do we have? We know that n is balanced by the force mg cosine alpha, so mg cosine alpha, so that's equation number 2. What else do we have? We have the gravitational force component, the tension, and of course never forget the friction along this side. So we have T minus mg sine alpha, and for friction we have mu n, so we have minus mu times mg cosine alpha, okay, and that should be equal to small m times a. So this is our equation number 3. So from equation number 1, what we find is T equals m times g minus a. So for example, T goes to that side, ma comes to this side, T loses a minus sign, ma gains a minus sign. So yeah, that looks pretty neat. And if we substitute that into 3, so let me call this equation number 4. If we substitute that into equation 3, what we find is m times g minus a minus mg sine of alpha minus mu mg cosine of alpha equal to ma. So of course we have a negative ma. I can take it to the other side. So what we have is capital M plus small m times a equal to, what we find is we can factor our g, and that gives us m minus small m sine of alpha minus mu small m cosine of alpha. Finally, we have a equals g divided by capital M plus small m times capital M minus small m sine of alpha minus mu m cosine of alpha, which is the acceleration of the system. If you substitute this into equation number 4 and simplify a bit, that will give us the expression for the tension as well. We can use this to see that the acceleration is constant, and we can also find out the velocity at some circumstance given an appropriate initial condition, and the same can be said for the distance as well. And I think that is pretty clear from the kinematics section from your book.